Hello, and welcome to Ants Are Everywhere. This is a live show where every episode I jump into a code base that I'm not familiar with and dig around and see what makes it work. This week we're looking at two graph databases. One is Neo4J, and the other that we're going to look at on Friday is called Janus Graph. Now, my original interest in graph databases was I had some graph data that I wanted to stuff into a database. And so this was something that I was looking to use for an app I was building. But when I started looking into it, I saw that there was some research indicating that I may not need a graph database, that ordinary relational databases, like we looked at last week with Postgres and SQLite, can perform well on graph data as well. So I'll show you this this paper here. It's by some people at IBM and Google. And what they did is they just created a certain schema for a relational database. I believe they used Postgres, and they compared it to the performance of databases, including of graph databases, that is, including for Neo4j and Titan, which was Titan's the predecessor for Janus Graph, which we're going to look at on Friday. So I don't know this research field super well, and I think that for my needs, as things are starting out, I'm not going to have a ton of data, and probably I only need to do a limited type of queries. So I'm thinking that perhaps I may not end up using either Neo4j or Janus for my particular application. Nevertheless, I would like to see how they work. And in particular, if there's anything really interesting about them, either the way that they store the data or the way that they think about and optimize queries that doesn't seem like it would port over to some use case I have. And just for fun, we were talking on the Ants Are Everywhere Discord channel, which you should join, and I'll put a link in the comment, the show notes. And somebody had suggested looking at connected papers and semantic scholar for doing essentially branching out to do a literature review. And so I popped this paper in there in these just to get a sense of what other research has been done on using relational databases for graph data. And it seems like there's a bunch of stuff. A lot of it's from like the 2015, 2016, 2017 era, which makes sense. I think that was kind of around the time people still believed in the importance of the semantic web. But there's lots of good stuff in here which you could check out. And then Semantic Scholar has things like papers that cite this paper as well. All right, so that's the research stuff. Like I said, I'm not a database researcher. I don't know this field well. I don't know this research well. And it seems like there are limitations to when you can use a relational database for this, but that's it. The cost of setting up a second database with a completely different model is, I think, big enough that it may make sense to start with using a relational database as a property graph. And maybe it's worth pointing out that if I understand correctly, one of the things that something like Neo4j does that's different from like a triple store, like an RDF triple store, is instead of storing like triples of like what is it, subject, object, and some sort of predicate of the sort that you see kind of in stuff like Prolog. There are a lot of databases that store those RDF triples and then use something like Sparkle to query those triples. And I think that's how things like Wikidata work. But a property graph is slightly different. Instead of storing triples, you store something more like n-tuples, where every node in the graph essentially gets its own object, which you can think of as kind of like something like a JSON document, and that object has properties that are stored in the node. So those properties in an RDF graph would be encoded in a series of triples, And then to add like annotations, et cetera, you'd have to have new nodes to map to the annotations, et cetera, et cetera. And so in an RDF graph, adding these properties kind of explodes the number of triples you need to store. Whereas in a property graph, that that logic is there's less data to store, and at least in theory, it's easier to iterate over that data than it is when you have tons and tons of triples, many of which are not really the heart of the concepts you're trying to encode. Okay, so that's my little spiel on the meta question of whether you might need a graph database. So here's the GitHub page for Neo4J. It's 70% Java, which is a little bit surprising because that means that there's about 30% Scala, which I was not expecting, but there we are. And it's not immediately obvious where things are. I'm going to guess things are in community because I think that this is specifically the community version of Neo4J. Let's maybe double check that. The community edition. So there's this open source community edition. It's basically an open core model. And then there's an enterprise edition, which has enterprisey stuff. And it's not clear to me, given that, for example, a database like Postgres could be used for small enough graphs. By the time you need something like a separate Neo4j style graph specific database, you may already be needing the enterprise features. So it's not clear to me if whether this community niche, whether this community edition occupies an important niche. And I guess one more thing I should say is that the thing that makes relational databases like Postgres pretty good at graph data is just that the optimizers are so good. And so if you watched my video on Postgres, we took a look at the optimization code. And if you haven't watched my video on Postgres, you should go back and watch it. So I'm in the community folder, and I'm not really sure what to expect. I think I've heard of Bolt. Let's see if Bolt is a Neo4j thing. An application protocol for the execution of database queries via a database query language, such as Cypher. So an application protocol. So it's some protocol for talking to the database over Cypher. So I'll ignore that. Boot check, I'm pretty sure I can safely ignore. Capabilities, I'm guessing I can ignore. Code gen, probably. Collections might be important. Let's open collections. Command line, I will ignore. Common could mean anything, but if it's common, that might mean it's central in some sense. Concurrent, I'm guessing is important for performance, but not as much on a first pass. Consistency check, I guess similarly. CSV could be comma separated value support. Exporting the CSV files. I'm not sure. Do we get a README? No. CSV reader. Yeah, I'm going to guess that's just CSV import essentially. Cypher is their query language, which I'll ignore. DBMS sounds pretty fundamental. Fabric, I don't know what that is, but we'll see, at least see what it is. Test, this is some sort of tests. We have a graph algo, which is probably important. Graph DB API, which might be interesting, but I have a feeling it's going to be hard enough figuring out where the code is that it may not be the best use of my time to look at the API just now. And then index could be support for database indexing. The kernel API, not sure if this is the kernel of the operating system or the kernel of the database. Layout might be important. Lock and logging, I'll skip. Lucene index. So perhaps they must have some support for Apache Lucene, possibly as an index into the database, given the name of this folder. Actually, let's see what we could find. Neo4j Lucene. Full text search index. Used index nodes and relationships by string properties. A full text index allows you to write queries that match within the contents of index string properties. For instance, the range of text indexes described in previous sections can only perform limited matching on strings, exact prefix, substring, etc. Okay. So this maybe gives you more natural language style matching for stringy things that are in nodes and relationships. Monitoring is important, but I'll ignore it. Native, I will ignore. And we just have Neo4J community, which might be essential. Harness, I'm going to guess is test harness. Neo4J might be the most important thing. Who knows? I'll look at that first, I guess. Then we have some procedure stuff. Maybe procedure compiler and procedure are interesting. Random values, I'll ignore. Record storage engine might be fun. Schema and some server stuff, which I'll ignore. Spatial index is maybe important. Testing, token API, unsafe. Values, wall should be write ahead logging. Whatever ZSTD is, Z standard proxy, not sure. Okay, so where's the Neo4j folder? So here's whoa now. Here's Neo4j. And then what is Neo4j community? Let's pull both of these out. I'm going to guess community is less interesting. And so I'll look at it first. You have a folder. And it's like the same stuff that was in that other folder. CSV, Cypher Shell, etc. So what does that mean? I don't know. Is this just a link back to the... Whoa. Yeah. Oh, sorry. This this is just the up directory thing. All right. Whatever. Okay. Here's source. Okay. So we have DBMS and GraphDB and server in here. We have community database state, system graph, identity, database, and API. Maybe let's look at database. We have things like abstract, database, context factory. This definitely looks like Java. We've got factories and we've got components and listeners and life cycles. So this seems like this is managing a database connection. What about, we have state. Let's look at state real quick. What year is this copyrighted? Oh, Sweden. I didn't realize they were Swedish. Do we have a year? I'm not sure. Okay. For some reason, the fonts are really ugly. Okay. So this is just a small, what the database, I guess, has failed. Something to call, I guess, on failure, an identity for the database. So there's not really much interesting in this directory as I imagined. Didn't I pull? That was both of them. All right. So let's kind of go through this. I've laid out a path for us. Let's go through this and see if we can figure out what the fundamental directories are. Collections, I'm going to guess, is not so. We have diff set, which is maybe some way of storing a diff. We have some factories, pool and trackable, primitive arrays, range long iterator, raw iterator, dependencies, heap tracking object map. Let's look quickly at the heap tracking object map. It extends measurable, whatever that is. It extends heap tracking long object hash map. And it's got something about heap size, and somehow it's going to use this to make sure, I guess, the heap is not too filled up. All right, so that doesn't seem so important. Here's common. And now we're getting at things that look more databasey, like cursor. Exceptions, function, hash, internal, kernel, scheduler, server, string, time. Let's maybe look at kernel. More folders, database, database factory, database ID, a UUID generator, and a database name. Okay, so database is not so interesting. Lifecycle is presumably just kind of the life cycle of the database connection. So we have initialize, start, stop, shutdown. That's not so cool. What else? We have memory. Let's look at memory. This is stuff like heaps and high watermark, which we saw some of this. We saw some similar stuff when we were looking at Bazel. So I wonder if this is common in Java, that it gives you kind of good access to the memory, probably of the virtual machine, the JVM. I don't know. And we have scheduler, which might be interesting. Let's look at scheduler. You've got groups and jobs and job handles and job types. What job types are there? Is this like an immediate, delayed, or periodic? So I guess you can do some things immediate, like probably a search. Delayed, I'm not sure what that would be for, but periodic is for things maybe like cleaning or reorganizing, compacting. I don't know if Neo4J has any sort of compacting operation. Is there anything interesting in cursor? Let's look at raw cursor. A cursor is an object that moves to point to different locations in a data structure. The abstraction originally comes from mechanical slide rules, which have a cursor which slides to different positions on the ruler. That's an interesting history fact. I was not aware of that. Each position in a cursor points, so it points to a row, just like in an RDBMS. Access to the current row is done by subtyping this interface and adding adding accessor methods. So I guess if you want to allow access to your thing, then you need to subtype this. And it's an interface that takes a type as a parameter. And I'm not sure if it's the type of a row. Move the cursor to the next row. So you can go next and you can close it. And that's basically it. Okay, so that's what a basic cursor looks like. What is a cursor value? So it's parameterized by t, and you can set the value. And you can get it, and you can invalidate it. Okay, that's really simple. So what's in common? Panic, dependency resolver, maybe is this for like dependency injection type stuff? Tries to resolve a dependency that matches a given class. Yeah, I'm not really sure what that is. I think that's more Java-y than database-y. We have subject and validator. Entity type. Let's look at entity type. You can be a node or a relationship. All right, well, there we go. All right. So actually, now that we have something mildly interesting, let's go look in Emacs and pull up this file. So let's see if we can find things that are relationships. And so where do we see them? We see them in representation type, representation. Something about locks. More stuff about locks. Resource type, which I think is where we are. Exceptions. It's in the Cypher implementation. JSON codec. How about relationship representation? Oh, this is REST. That's just like representing it as a REST thing. Okay. Neo4j types in the API. Random schema base. Storage cursors. So it's in the storage engine. Constraint type identifier tokens. Truncated query snapshot test. I don't want tests. Procedure compilation. Yeah, it's hard to figure out what is interesting here. I'm going to guess that. See if we can find. Let's look at the storage thing. Should we? Let's look at the kernel API. Use provided cursor for properties on relationship load. That's like a full sentence. And this is some mock stuff. So this is a test. I don't want tests. What happened to my xref? Here we go. All right. So let's try Neo stores. the relationship store. So if you call get relationship store, then it just calls get store on type relationship. Well, that's pretty simple. Is there anything interesting in the imports? We have internal helpers, page cache, kernel implement store format. Okay. Runtime exception, close store. We can flush. That's not so interesting. So where's the interesting stuff? Let's go back to GitHub. I feel like we're just, we're in like fluff land. All right, here's DBMS source. Command line, I'm going to ignore. I think database should probably be about database connections again, right? We have database info and info provider. Routing, is routing interesting? We have availability checker, rich routing result, server side. And this is like server client stuff. Operator state. We've got a description of the operator. Okay. So where is the diagnostics database state? Not so interesting. Okay, fabric. We have a query router. Does the router do any optimizing? I'm not sure. Let's see if ChatGPT will tell me where the cool stuff is. In the Neo4J community code, let's first ask for query optimization. The Cypher compiler, okay, that makes sense. The query planner. Okay. So maybe I do want to be in the Cypher land. So let's look in Cypher in just a second. Here's graph. Let's look at graph algo. This must be fun. Basic evaluation context, something about some context, cost evaluator. I want to see that. Okay, let's pull this into its own thing. Okay, so cost evaluator and cost accumulator. Maybe accumulator is just accumulating stuff. Here's a graph algo factory, a pathfinder, and a weighted pathfinder. This should be pretty good. Shortest path, we have Dijkstra with a priority queue, Floyd-Warshall, single source shortest path, etc. This is fun. Let's pick one of these. Maybe Floyd-Warshall. And what was that? Shortest path? Here's path. We've got, okay, so we've got things like A star. So these are standard now graph algorithms that you would see if you were, taking an algorithms class or studying for a coding interview. And then where am I now? So here's util. So the utility has stuff like whatever a Dijkstra selector factory is, double adder, Fibonacci heap. I think that's the second time I've seen a Fibonacci heap in the wild. Path implementation, whatever that is, a priority map, weighted path implementation. So let's just look at a few of these and see what the code feels like. All right, so cost evaluator just is a single interface. It's got get cost. So I guess you have to implement this to do anything interesting. Will this tell me where the references are? Search for this symbol. All right, it doesn't want me to search for this symbol, but I will in Emacs. So let's look up. Can I call xref find references without being on a code point? Okay, so here's cost evaluator. And it's used in things like Dijkstra and A star. Okay. In fact, let's look in Dijkstra. So what is the actual implementation? So you pass in a cost evaluator into Dijkstra. Okay. So we've got this public Dijkstra thing. We finally have a little bit of code here. Was it like 80 lines? 184 lines? Just starting at the bottom because I'm here. We have this evaluate function. We're just going to return an evaluation. Not sure what an evaluation is, but you give this function a path and a branch state, which is parameterized by a double, or it's branch state of double. And the state, I guess, is responsible for like where you are in the graph, potentially, because the first thing it does is it gets the state. And if the path length is, or rather maybe state is just like the state part of the state machine. I'm not sure yet. And if the path length is, non-trivial, bigger than 0, then we're going to set the next state to be, we're going to add the cost evaluator of the last relationship we saw in the path and set whatever this is to outgoing. Then we're going to set the state to the next state. And if the path end node equals whatever end node is, maybe this is the real final end node somehow, then we're going to set shortest so far to next state. And we're going to return include and prune, which will, I guess, tell you to include and prune some stuff. And if neither the path length are above 0, nor the end node is the path end node is equal to the end node, then we're going to say to exclude this path, I guess, and continue. So I think this is basically saying it's a dead end. And this is saying it's not a dead end, but also prunes some stuff. And I missed this min here, which is good because I was confused about why we were doing this. So we're going to set it to the min of whether if we're shorter than the shortest so far, then we are now the shortest so far. Otherwise, it's just the same as it was before. Okay, so this is finally something interesting. Path last relationship. I'm just curious what's the thing? What the last relationship is. I'm guessing that like as we traverse an edge, we keep track of what the relationship was. Is this the definition? This can't be the definition. Okay. So it's a relationship value. Oh no. So relationship value extends virtual relationship value, which sounds like a virtual relationship sounds like something you have with a cyber pen pal. And it implements relationship visitor. Let's look at relationship visitor. Okay, and where are we? We're in storage engine. I guess storage engine is where the cool stuff happens. Okay, so the relationship visitor just has a this interface home with some stuff about exceptions and a method visit. And if you're a relationship visitor, then you have a visit function, which is going to take a relationship ID, which I guess is like an identifier for that edge in the graph, a type ID, which I suppose is like, can relationships have types? I guess they can. And a start node and an end node, because this is a directed graph, I guess. We have the start and the end. So let's look up, can Neo4J relationship types. Without relationships, your type definitions are simply a connection of disconnected nodes. Oh, I guess the type might be things like acted in. So Tom Hanks acted in movie. So he acted in movies. Or maybe the type is like from actor. Maybe the type is like it would be in something like Haskell, where it's a map from Haskell. Sorry, from from person to movie. At any rate, okay, let me just ask ChatGPT, what is the type of a relationship in Neo4J? Okay. So in this query, I'm going to ignore everything it says before this paragraph. So P from person to person friend of represents a pattern where the person node is connected to another person node via the friend of relationship. Okay. And you might write a query like this, match P person friend of, etc., where P.name is Alice, etc. Okay. The type of relationship is defined by a label, which is a descriptive name used to categorize and distinguish different types of relationships. Cool. So that's what a type is. Oh wait, I was in Emacs, right? Okay. So that's what visit does, which is cool. So a relationship value is a thing that can visit, and it has an ID and a start node and an end node. And does it just attach a value to the relationship? So you're going to give it those things. We've got this extends exception. Oh wait, no, what is this? So write to. We can we can give it a value writer. It might throw an exception. And if the write entity mode is reference, we're going to write the relationship reference of ID. Otherwise, we're going to write a bunch of stuff, including the element ID, the start node ID, etc., and like whether it's deleted. So like write all the metadata. Okay, we've got this toString thing, which is consistent with what ChatGPT just told me was the format of a relationship. And what makes this a relationship value? We've got a type, which is a text value. We've got properties, which is a map value. And when we visit it, we just set the type to whatever the type is, which is a little bit odd. And we've got a direct relationship value, which is probably why it's a value, whatever Jamal call it. And this is maybe basically the property graph implementation, right? So we've got a properties, which is a map value, which I'm going to assume means it's essentially like a dictionary. So we'll look at what a map value is in a minute. A direct relationship value. Properties are the properties of this relationship. And that's the map value stuff. Okay. So, and estimated heap usage of a relationship. How much heap space can a relationship really use? Okay, so I'm going to guess that the thing that makes this a relationship thing is this map stuff, which is essentially the thing that makes it Neo4j a property graph as well. So maybe that this is finally something really central. So a map value is a thing that you pass in whatever KV is. It just takes an object, which is like the any type, I think, for Java. This is a test. No, I want the real thing. I want the real thing. Yeah, public abstract class. Extends a virtual value, of course. So we've got a key set, which is going to give us some iterable. We can map over everything with for each. We can have some contains operation. We can get a value from the key, etc. And we can estimate the heap usage. Map wrapping value. And so a map value is a map value that's implemented using a Java map. What else do we have? A filtering map value, which has got a by function, which is a filter. Okay. Mapped map value. All right, different kinds of maps that are, I guess, optimized for different relationships. So that's what a path value is. So let's look back at Dijkstra. Let's go to the beginning. All right, we've got a path expander. I'm not sure what that is. I'm curious enough to look at it. An expander of relationships. It's a flexible way of getting relationships from a path. Given a path, which relationship should be expanded from it to traverse further? Okay, so this is like you're in a graph algorithm, and you want to know which other paths you should look at, and so that's abstracted in this path expander interface. And then we've got initial branch state. We need a cost evaluator, which we've seen used. I don't know if we saw it defined yet. A traverser. So we're going to expand paths, and this should be some strategy for traversal, but exactly how, I'm not sure. Let's see what its methods are. It extends iterable, represents a traversal in the form of link nodes. Oh, wait, no, of nodes. Link is just the Java doc thing, right? So this is a convenient way to iterate over paths. Okay, so what can we do? We can get the nodes, which will return an iterable. You can get an iterable of relationships. Yeah. We can get an iterator, which represents the traversal in the form of paths. When a traversal is done and haven't been fully iterated through, it should be closed. And metadata. So basically, we can get the list of nodes to traverse over, or the list of relationships to traverse over. And we can get some iterable thing. Okay. Epsilon. I'm not sure what epsilon is for Dijkstra's algorithm, but okay. So we're going to pass all this stuff into the constructor. We've got this find all paths thing, which is going to take a start and an end. And it's going to set the traverser. And it's going to return a new weighted path iterator. Oopsie. So what is a weighted path iterator? It's going to be a path iterator weighted by something. By what? Probably cost epsilon. And what is interest? We have a path interest factory. Huh. It's like a path interest. Path interest decides if a path is of interest or not in priority-based traversal. Okay, so whether the path is interesting for things like Dijkstra or A star. So we've got, I don't know what I keep pressing to bring up the Emacs thing. So we've got the comparator. Whether something can be ruled out. Decide if a traversal branch with number of visits, path priority, and old priority can be ruled out from further traversal or not. All right. Whether it's still interesting, and whether to stop after lowest cost. So the traversal stop when traversed beyond lowest cost. And so do we have implementations of this? Visit count based path interest. And this will use number of wanted paths to decide if an entity should be ruled out or not, and if an entity still is of interest. So this is all lots of stuff. So I'm wondering if one of the advantages of using something like Neo4J is that they have worked out this way for you to iterate, do kind of standard graph algorithms, but in a flexible way and in a canned way so that you don't have to implement them yourself. It's possible that that's the sort of thing that's going on. I don't know. Okay, so let's see what else is in. So we have the traverser, which is the one we use here. And this has got to implement some methods, right? We're going to set blah, blah, blah. Shortest so far to the max value. We're going to set Dijkstra expander to be whatever this new path Dijkstra path expander is. We're going to set the path evaluator to the Dijkstra evaluator. And then we're going to have a monodirectional traversal description is the last traverser. What are these things? I don't know. Let's look at monodirectional. What makes it monodirectional? Traverser iterator. I guess it just goes in one direction, right? All right, whatever. But what is the, let's look at the Dijkstra path expander. The path expander is just setting some stuff. Oh, wait, no, we've got some implementations down here. So when we do expand, what we're going to do is compare the state and the shortest path so far with epsilon. And since these are doubles, I guess the idea here is that epsilon is controlling. You never get exact equality with 0 for doubles because of numerical imprecision or whatever that stuff is called. So I guess epsilon is controlling like how close you need to be to equality, and then we're going to tell it to stop after lowest cost. And if this, so if the compare is bigger than 0, and we need to stop after lowest cost, they're going to return the empty iterable, it looks like, empty resource iterable. Otherwise, we're going to call expand on the source with the path and the state. So expand is really just doing this final check, this finality check of whether we're done, essentially. Reverse is going to revert, I guess, source reverse, since we are in a directed graph, this seems to reverse the direction of the arrow. I'm not sure why you want to do that, but maybe you have to do that in Dijkstra's algorithm, and I don't remember. And then we've got an evaluator. And what's it going to do? We've got this evaluate function, and I think that's what we read at the beginning. Yeah, okay. So where does it, whoa now. So where does this cost evaluator come in? Where is it like, oh, it's just passed in. It's not defined anywhere in here. Okay, so that's interesting. That's taken us to a lot of, it seems like how Neo4J is thinking about graphs. Is there anything interesting in Floyd-Warshall? We have cost type. So we have two possible different cost types. One is start cost, which is the starting cost for all nodes. The other is infinitely bad, starting value for calculation. So everything in Floyd-Warshall starts at basically, what is it, like negative infinity or positive infinity, I guess, if it's cost. And we have some stuff about directions. We have the cost evaluator and a cost accumulator. Okay, and so all of this is standard graph traversal stuff. And so yeah. So where is it used? Is this just for if you want to use Dijkstra on your stuff? Or does this get used internally? I don't know. But let's plow along. Here's the graph algo factory. Pathfinder returns an algorithm which can find all available paths between two nodes. These returned paths can contain loops. That is, a node can occur more than once in any return path. So if you ask for Pathfinder, you get all paths. You can ask for all simple paths, shortest path, but how do you tell it whether to use something like Dijkstra or whatever? I'm not sure. And then what's an evaluation context? It's just got a transaction and a database service. So I guess it maybe like whether we were under transaction and like what is the database handle thingy. Okay, so here's Pathfinder. I think we looked at Pathfinder. I'm going to ignore that. Weighted path should be weight. It extends path by weight. So it's just a path with a weight. And we looked at Floyd-Warshall briefly. I don't think A star is going to have anything fundamentally new, but we'll look at it quickly. Cost evaluator, estimator, etc. You can give it two path will take a node and a list of relationships. And we're going to create a builder and give the path to it. Then we're going to iterate over the relationships and push them on. I don't know why you need that, but that's something you might need. Use Fibonacci heap. At least a partial implementation of a Fibonacci heap, a priority heap. Almost all code is based on the chapter about Fibonacci heaps in the Corman book. Yeah. Okay. Amortized times for almost all operations are O of 1. Extract min runs an amortized time O of log n. That's nice. Which then a delete based upon it also would. It can store any data type given by the key type parameter. Okay. So they just copied that from a book, which is a good strategy. Ooh, hey, this bird has been charged. How goes it? Yeah, it has. All right. And here's graph algo impl. What is it? I don't know. I think that this should be really close to what we saw. We can take relationship to a string. We've got this path implementation, etc. Start node, end node. Working so on your third monitor. Cool. That's the way to do it, I think. I don't know how I would do 3 monitors. Are these like does it take up your whole field of view? Thanks, dude. This bird has been charged. The bird has been charged says, all good. Keep up the good work. I watch these at night. Awesome. Thanks, dude. I appreciate it. All right, so now where are we? We've seen graph algorithms, which is good. We've seen some stuff about how Neo4J encodes relationships. Nodes, I don't think we've really seen, but a node should just basically be any object with some data attached. We've seen the node object, but I didn't look at it because it didn't seem so fundamentally important. But what I don't know is yet how things are stored on the data. Sorry, on disk. And I don't know. Is that what I want to know? Maybe that's what I want to know. Should we look at Cypher? Interpreted runtime, logical plan builder, physical planning. Let's look at physical planning. Scala. All right, here we go. Physical planner, Scala, physical attributes, pipeline breaking policy, slot allocation, top level argument, tree builder. Let's look at physical planner. I don't know if I know how to read Scala. Something called semantic table. AST semantic. Okay, so we've got some abstract syntax tree, which makes sense. And we've got some stuff with logical plans. And plan is going to take a whatever a token context is. We're going to set whatever, I don't know, before write semantic table breaking policy config. And we're going to, I guess, return a physical plan, if I understand this notation correctly. Ready to go. So this is presumably declaring a variable called result that has these things set. And we're going to, whatever expression variable allocation, we're going to allocate before write. Slot metadata, slot allocation allocates slots. I don't know what a slot is in this context. Then we've got a slided writer, some debug stuff, and then we're going to return a physical plan with a final logical plan, expression slots, metadata. So let's, whoa, no definition for physical plan. Here. Yeah, so the bird has been charged saying, wouldn't IntelliJ help to grok the code a bit more? This is maybe. maybe I just didn't tell it to build tags for Scala. Maybe that's the I mean, it was doing just fine on Java. I don't even know if I can build tags for Scala. Should I try it? Does that syntax work? I know language Scala. Okay. So it doesn't like Scala. And just in case I broke my tag file, I'm going to regenerate them. Okay, so a physical plan has a logical plan, something about expression slots. The number of expression slots, which is an int, some stuff about slot configurations, argument sizes, whatever apply plans are, nested plan argument. So let's look at logical plan. No definitions found. Come on now. Let's look at slot. A slot sealed, I think sealed is a essentially this is basically a struct. So slot is an offset, whether it's nullable. A cipher type is type compatible with other slot and long slot. So maybe things are stored by type. Let's look up, get out of here. Let's look up on the internet. Neo4J slots. I have a feeling that DuckDuckGo is ignoring my search terms here. We have a knowledge base. What is that? A composite index. Okay. We denote a tagged property of a composite index, a slot. For example, an index on person has 3 properties and thus 3 slots. So first name, surname, and age are the slots. So person is essentially a node in the graph, right? And so we talked about how this is a property graph. And so in the SQL relational to graph paper that I had up in the beginning, person would be, I think, literally a JSON document. I believe they were using JSON documents in Postgres for the object properties. So I think that a slot is basically the number of fields of the thing that would be a JSON document. In the index, each slot is filled by an element. In order to calculate the size of the index, we must have the size of each element in the index, i.e. the element size as calculated in previous sections. The following equation can be used to verify that a specific composite index entry is within bounds. The sum of the element sizes is less than or equal to 8167. Shouldn't the less than sign be on the other side? I'm not sure. Okay. So here's some stuff about maximum arrays. All right, so that's slots. And so here the slots have an offset into what? I don't know. I don't know what it means to be nullable. I guess, the name of a person is maybe not nullable, but their apartment number might be or something like that. A type, that makes sense. Whether it's compatible with some other slot. I'm not sure what compatible means, but we've got things like long slot. Is that for storing longs? We've got ref slot. Is long slot make string. Ref slot with alias. Okay, so slots. We can allocate slots. We've got some AST stuff. ID from slot is empty, is primitive null, non-empty. Okay, relationship from slot. How do we get a relationship from a slot? We call it is canonical value or something. No, we're overriding this. I'm not sure. I guess we're setting name equals name. Okay. So that's physical planning. Where's logical planning? Logical plan generator. And we just have tests. Is there nothing but tests? Let's go into the tests. We've got a cardinal. Let's see. Do we import anything logical? We have things like cost model monitor, metrics, cardinality cost model. Yeah, all that seems important. Aggregation, all node scan, anti-semi apply, apply argument ascending Cartesian product, distinct eager, I'm guessing eager evaluation, exhaustive limit, expand, index order, limit. So are these like, is limit like the SQL limit? Sort top. So let's look at Cartesian product just for fun. This is exceptions, notifications. I think it's unfortunately that my editor doesn't understand. Maybe Cypher logical plans. My editor doesn't understand Scala. Okay. Let's try this. If I can get rid of the delay on YouTube. What's the delay? You mean when you type versus when it appears? Or is there another delay? Okay, so I see some Cartesian product stuff. Unnest Cartesian product. IDP. What is IDP? Cartesian ordering. So this is in compiler. Okay. So this is interesting. Cartesian ordering. So how did I run find? Here. Did I ask for only Scala files? Whoops. That's not what I meant to do. All right. Let's try one more time. Oh, no, I want to find Dured. Yeah, okay. No, I did not ask for just Scala files. Okay. Let's try plans unnest Cartesian product. It's going to extend rewriter. Whatever this top-down thing is, we've got this left-hand side and the right-hand side. We've got an apply function. What is it doing? That's what I want to know. And how do I get to this thing? Cartesian product. Yeah, I don't know. I haven't asked for a delay on YouTube, I don't think. I think it just might be inherent to the way that they build things. But I'm not sure. I can check next time. Next time I'm before I go. Yeah, so I'm not. It's not finding. I don't know enough about Scala to know where to find this plans argument, or maybe Cypher internal logical. How do here's the package. Plans rewriter. Let's just go to plans. Is that where we were? Plans. So we've got a rewriter. And so I guess one of the things it's going to do is rewrite your query. Is that the idea of a rewriter? Remove identical plans, simplify selections, skip and partial sort, unnest apply, unnest Cartesian product, use top. Okay, and so what's a simple one we can look at? BFS depth order, BFS aggregation remover. Let's look at cardinality rewriter. Did we look at this already? We've got post conditions, preconditions. So here are the preconditions. The compilation contains a logical plan. This should happen after finding the final plan. So we found a final plan, but we're going to, logical plan rewritten is a precondition. Logical plan contains eager if needed. Okay. And so change logical plans to reflect the effective output cardinality. And so how are we going to do this? We're going to create this instance with a planner context, whatever solved is, some cardinalities, effective cardinalities, provided orders, label and type and row other attributes, and anonymous variable name generator. And we're going to set the rewriter to be record effective output cardinality. And then we've got some post conditions. And I'm not sure what's actually, this seems like just wiring stuff up. So where's the implementation? I don't know. Something's going to call this. I can't figure out what's going to call it. And we're already over an hour. So I'm not going to dig much deeper into that. But I would like to know what the storage model is. So let's see if we can find Neo4J storage format. Understanding Neo4J's data on disk. This seems useful. I'm going to move this chat off for just a moment. So our persistent storage for long-term durability. Okay, that's good. They're located in data databases GraphDB. And the node store stores node data from your graph. Relationship stores data related to the relationships. Properties are stored as key value properties and label. It's a schemaless database. Okay, so we use fixed record lengths to persist data and follow offsets in these files to know how to fetch data to answer queries. Okay, so they're using fixed length records and they're just indexing into a record, I guess. So for a node store, a record is 15 bytes. And for a relationship, it's 34, which is double 15 plus 4. You would expect it to be roughly on the order of, you should at least be able to refer to two nodes, the beginning and end point, and you need a label. So it's not so surprising that it's a little bit more. Property store, the record is 41 bytes. Properties for nodes and relationships, but what are the format? A property record has a payload of 32 bytes, which is divided into 4 8-byte blocks. Each field can hold either a key or value or both. Okay. The data stored on disk is all linked lists of fixed size records. Properties stored as a linked list of property records, each holding a key and value and pointing to the next property. Each node and relationship references its first property record. Okay, so everything is stored as a linked list. I'm not sure how they came to the conclusion that that was the thing to do. Maybe that's a totally reasonable thing to do. I'm a little bit surprised by it, but maybe I shouldn't be. I don't know. What about indexes? Each index entry, okay, is an index also a linked list? Let's ask ChatGPT. How does Neo4J store data on disk? I'm guessing that it'll tell me basically what I just read. So they're stored in node store as key value pairs, well, associated with a node ID. This allows for fast access. Relationship stores, property store. Yep. Okay. So is everything stored in linked lists? Nodes and relationships are not stored as linked lists in the traditional sense. Instead, they are stored in data structures optimized for graph processing. Nodes and relationships are assigned unique IDs and stored in specific files that allow efficient access and traversal. But didn't this just tell me everything was a linked list? Not this one. Data is stored on this linked lists of fixed size records. All right. I don't believe you, ChatGPT. Let's ask Bard. Bard usually doesn't know about coding stuff. But hey, look, Neo4J stores data on disk in a linked list format. This means each node and relationship is stored as a linked list of records, each of which contains a fixed amount of data. The linked lists are stored in order, and each record points to the next record on the list. I guess maybe linked list makes sense if they're linked in order of if their link has something to do with they're linked in some sort of traversal order. So we've got the node store, the property store. It's a very efficient way to store data in a graph database. It allows Neo4j to quickly and efficiently access data, even for large graphs. If you were designing graph database, what data structure, how would you store data on disk? So Bard says that they would use a linked list format. They're having to search through a large table or document. But isn't it still a linear search? So it's very scalable. You can simply add more nodes to the linked list. Okay. Let's ask this question to ChatGPT as well. Okay, so I will also ask what format does Janus graph use for disk storage? You're not going to commit to anything? I don't think ChatGPT wants to commit to anything. So Janus graph uses an adjacency list to store to format an adjacency list format to store data on disks. So it's basically storing the graph structure. This means that each vertex is stored as a row in the underlying storage backend. So Janus graph uses a separate storage backend, like Bigtable or something. Or you can use, I think, Apache, Cassandra, or HBase. And the row contains a list of all the vertex's incident edges. Each edge is stored as a separate cell in a row. Okay, so I'll ask the linked list in Neo4j also encodes an adjacency list. So Bard's saying yes, the linked list in Neo4j also encodes an adjacency list. That means that each node in the linked list represents a vertex in the graph, and each record in the linked list represents an edge that is incident to the vertex. Okay. All right, that seems reasonable then. The following linked list represents a graph with two vertices. So node A, edge to B, and then node B. Okay, and then the last question I'll ask Bard, since Google, at least one of the authors on the SQL paper was from Google. I think the other two were from IBM. I'll ask, what can you tell me about the research on using relational databases for graph data. I've seen that in some cases, a traditional, I'll say, RDBMS can outperform a special purpose graph database on graph queries. So there's been some research, yeah. So then in some cases, this is what I told you. One reason for this is that it's optimized for joins, which are a common operation in graph queries. Graph databases are also optimized for joins, but they are not as efficient as relational databases. Another reason for this is that relational databases can be more scalable than graph databases. They can be partitioned across multiple servers, while graph databases are typically limited to a single server. Oh, I did not know that you couldn't really typically horizontally scale a graph database, although I think the same is kind of true of traditional databases, right? It's not obvious how to scale something like MySQL or Postgres without additional stuff, I think. However, there are some disadvantages. Relational databases are not as flexible because they store stuff in tabular format. Not as easy to use for graph queries. Here are some research papers I found using relational databases for graph data. Thanks, Bard. This is not the right paper. External definability in groups and in IP theories. This is logic. Okay, cool. What are the chances that this is the right paper? Sparse Bayesian dictionary learning with Gaussian hierarchical model. Cool. There's nothing to do, nothing to do with the topic. And integrals of motion for one-dimensional Anderson localized systems. This is kind of cool. This is maybe a good way to generate random archive links. All right. So the last thing I'll ask is, if I want a horizontally scalable database for graph queries, should I use RDBMS as suggested by some of these papers? Or should I use something like Neo4J or Janus graph? So they're saying Bart is saying I should use Neo4j or Janus graph because relational databases are not as efficient for graph queries, which is empirically false for some graph queries, but it's probably true in general. Okay. All right, cool. So that's it for me. I still feel like I don't really understand what's going on with Neo4j. Their layout, their code layout is very Java-y. Hi QSM. Their code layout is very Java-y. So a lot of the files are doing things like wiring things up. And then they also have a lot of like special purpose terms like cipher and bolt. And it's not as clear as it was with something like Postgres. Like, where does the optimized stuff happen? Is that cipher specific? Is there like general purpose? Like if you queried Neo4j with Gremlin, which I think you might be able to do, does it run through the same query optimizer? I'm not sure. Imagine Java. So there's that, but we did find some places where they go through some of the standard graph algorithms, and all of that code was relatively clear. Although arguably overly abstracted, kind of in the standard Java style. And then the Scala code, I wasn't sure how to navigate it properly with Emacs, and I wasn't finding some of the identifiers, like at least Emacs wasn't finding them, and I wasn't seeing what I was looking for, just doing essentially a grep. So that probably is because I'm not really sure how the Scala import system works. I was probably making assumptions that aren't really correct. But a lot of the Scala code that I did see seemed like, again, it was sort of like setting things up, and then it wasn't clear where the actual implementation details were. And it can be the case in some like really big Java style programs that the implementation details are kind of like all splayed out. Like there's an algorithm there to be seen, but the algorithm you can't really get by looking at the code. You have to essentially look at it in some sort of in like a debugger or something, because all of the classes need to be instantiated and subclassed before you finally get an object that has the right methods that are operating on the object, on the whatever you're passing in correctly. So if this were something that I were really closely considering using, I would dig into it more. But since I think I've narrowed things down to probably something like Janus Graph or Postgres for my needs, so I'm going to leave Neo4J for here. And yeah. And I'm seeing a suggestion for OSRM backend. I'll look this up. Open source routing machine. Is this related to OpenStreetMap? Yeah, I'll go ahead and add that to the fan requests. All right, so that's all for me. I'll be back on Friday to look at Janus Graph. And thanks for watching.